Welcome back. So we have been studying the various techniques for modeling of problems, and we were looking at the linear programming approach to model a problem. So basic idea is that given problems, if we can model it in another mathematical language, then it might be useful for solving the problem. There are various different mathematical languages that we have, and the usefulness of converting it or modeling it in a different mathematical language is that we can use the techniques from those mathematical tools to solve the problem. In this set of videos, we have been looking at how to model discrete problems using graph theory and linear programming. So we are doing it by looking at a few examples. In the last video, we looked at a particular problem which was an optimization problem. Now what is an optimization problem? So optimization problem is something where you minimize or maximize something like a cost or a profit under a certain set of conditions. Now this kind of problems arise a lot in real life, in industry and so on. Right? So in fact in the modern world, in the subject of big data and so on, we do have very obvious problems which are optimization problems. Now we have picked up 4 such optimization problems, and we will see how these 4 optimization problems can be modeled in language of linear programming and graph theory, and that would help us to solve the problem. Now, the first problem that we looked at, and this is something that we studied in the last video, is when we looked at the best way of loading 3 wagons using by 4 different kind of cargoes, when we have a restriction on the weight of where each wagon can carry and the space that each wagon can carry. Right? In this particular video, we will be looking at the second problem, namely bang for buck in advertisement. Now, what is this problem about? So, it's about the marketing budget. So, imagine that you are one of the big person in the marketing for a company. Now, you have been allocated 6 crore and 10 people under you. And your goal is to advertise your company in such a way that you maximize the amount of number of people that you reach. Now you can spend this 6 crore in different ways. Now here are the set of options. You can spend it on an ad during the Cricket World Cup. It would cost you 3.5 crore and the expected reach will be say 10 crore people. But for getting this advertisement working and dealing with various logistic issues, you need 5 people. Or you can decide to maybe sponsor the IPL, in which case you will have to pay 5.2 crore and you will expect to reach something like 15 crore people, but the number of people required to pull off this advertisement is 7. Similarly, maybe for ads in the FM radio, you will require only 0.1 crore and you expect to reach only 0.5 crore people, but the number of people required is just 3 maybe you can think of TV ads during peak hours or non-peak hours and so on. So you have these various options. Of course, your goal is to spend this 6 crore in such a way that this total expected reach is maximized and you don't want to neither overspend more than 6 crore, nor can you invest in things for which you will require more than 10 people. For example, you cannot expect to fund both Cricket World Cup and IPL. First of all, because you don't have that much fund. 3.5 plus 5.2 is way more than what your budget of 6 crore is. But also, this 5 plus 7 is more than the number of people that you have. But maybe you can spend in IPL and the radio ads in FM. So then the total expenditure is less than 6 crore and the total number of people required is just 10 people. Right? So, under all these circumstances, what is the best thing to do? What is the best way of spending this money? So, this is a typical optimization problem. One important thing here is that I cannot say that, okay, let me spend half, I will buy half an ad in Cricket World Cup. That cannot be done. Either I decide to invest in Cricket World Cup or not. It's a 0-1 setting. Similarly for something like in radio ads. It cannot be that, okay, I only spend 0.05 crore in video ads. No, you either spend 0.1 crore or nothing. So it is like you don't have an option of picking any one of these ad options partially. So you have to either go for it or not. And this is what makes the problem interesting. We'll see it soon when we look at this problem in a short while. So before I go on, so let me quickly talk about the other two problems that we will be doing in the coming videos. Namely, the problem number 3 is the telephone tower problem. You have n important locations in the city and you want to ensure that every of the n locations has good 3G connection. Now, for getting a good 3G connection, there must be at least one tower within the radius of 1 kilometer that has the 3G option. So, the company now has to decide to minimize the number of towers it wants to upgrade so that every location in the city gets the 3G option. What is the best or what is the best set of towers to upgrade? This is again another problem that one can imagine happens a lot of time in the telecom industry and similar industries. And we will be using our various modeling techniques to solve this problem. The fourth problem is this meeting scheduling meetings. So it's like an HR is trying to organize a collection of meetings in a particular hotel and they have to book certain meeting rooms and there are certain meetings that will be there. For example, the meeting 1 will be from 9 am to 11 am, meeting 2 will be from 10 am to 11 am and so on. Now if two meetings, for example meeting 1 and meeting 2 are in disjoint times, then you can have these two meetings in the same room, one after the other. But if there are two meetings, for example meeting 1 and meeting 2, and if they have a conflict in time, then you cannot have both the meetings in the same room. In that case, you have to book two different rooms. Question is that how many rooms do we need to book to ensure that there is no clash, everything happens perfectly fine. So this is again another example of a minimization or maximization problem. In this case, the minimization problem. We will be seeing how to model this problem also to get a proper solution. Now the common approach to all of them is the linear programming approach. The idea is that you maximize or minimize a linear equation, something like 3x plus 4y minus 10z, under the condition that some set of linear equations are satisfied. For example, 5x plus 8y is less than 15, or 7x plus y plus 8z is greater than 4, or something. So this is a typical instance of a linear programming. You maximize or minimize a linear optimization function under some, we call them as linear constraint. Now, a crucial part is that what are these x, y, and z? So these are variables, but are they taking real numbers? Can they take fractional values? Can they take only integer values, and so on? Now, the most simple one is when they take any value in the real numbers. And in that case, we call that one a linear programming. Now, usually we can use linear programming to model a quite number of problems. We saw it in the last video, how to use linear programming to solve the problem 1. The good advantage of using linear programming is that there are various nice packages in various software to solve linear programming. It's a very well studied subject. Of course, it is beyond the scope of this course to tell me how to solve a linear programming in its full glory. But there are packages or softwares or whatever that can be used to solve linear programming. So from the point of view of solving a problem, it's pretty much good enough to reduce a given problem to a linear programming, or use linear programming to model a problem. Right? So in the case of this language R, here is a way in which you can feed this linear program into the language and ask for a solution. And the best part of it is that linear programs, particularly when the values are taking when the variables are taking real values, they can be solved in polynomial time. There are nice software libraries that can be used to solve it. The biggest trick is how to model this problem in the LP form. So in the last video, we saw how one can use the problem, the LP to formulate or model the problem 1. In this video, let's look at the problem 2. Now, let's quickly recap what the problem 2 is. You have 6 crore in hand and 10 people, and you have to invest in various advertisement options. Each advertisement option has a cost associated with it and the number of people required, and each of them has an expected number of people it will reach. Your goal is to reach as much people as you can, under the condition that you don't spend more than 6 crore and you don't waste, or you don't need more than 10 people. Right? So what is the typical way in which we can start modeling it? Now, one way is that here we can decide, let x1, x2, x3, x4, x5, these options basically are saying that what is the probability, whether it is 0 and 1 is basically saying whether I am going to invest in this particular ad or not. So if x1 is 0, then that means that I am going to invest in Cricket World Cup. If x1 is 0, I don't invest in Cricket World Cup. If x2 is 1, it means I am investing in the IPL, and so on. Now, if this is the case, now what is the expected reach of people? Now, if x1 is 0, then the number of people I get reach is 10 crore times x, right? Like times x1. And if x1 is 0, I get 0. If x1 is 1, then I get 10 crore people. So we want to maximize the expected reach, which is of course this number, right? But we have some conditions. What are the conditions? Now, if I decide to spend x1, if x1 equals to 1, I have to spend 3.5 crore. If x2 equals to 1, I have to spend 5.2 crore. So that means we have to ensure that the total cost is met. Total amount of money that I have to pay is less than 6 crore, and which can be modeled using 3.5 times x1 plus 5.2 times x2 times so on is less than 6. And similarly, the number of people used can be modeled like this. Now, this is a very much of an LP problem. You have to maximize some condition, maximize this under some set of linear constraints, right? So we have to maximize some constraint under some set of linear constraint. But the problem is that these x1 to x6 are not real numbers. They are 0 or 1. So this is what makes it a bit problematic. When the numbers are 0 and 1, we don't know how to solve the problem easily. And in the language of algorithms, it is told that it is an NP complete problem, meaning we don't expect to get a very quick solution to this. So, although we have managed to convert the land problem into an LP formulation, but since the xi cannot take fractional values, hence I don't know how to solve this problem quickly. So I cannot expect to have a quick solution to this problem. So can we do something else? So the idea is that we can relax this integer linear program by saying that instead of having this condition of 0 and 1, that the variables are either 0 or 1, I can say that let this variable be between 0 and 1. And now it solves this problem. The problem is that it might give me an answer something like spend, so x1 equals to half, which means that okay, x1 equals to half, meaning in this case buy half the advertisement in Cricket World Cup, which might not be an option, which is not an option for me. So it's not a useful solution for my case if I get a fractional solution to this LP. Right? So if I have a fractional solution to the LP, I might get a solution like x1 equals to p1, x2 equals to p2, and so on till x6 equals to p6, where p1 to p6 are not necessarily 0 or 1, but some fraction. Now what do we do with this PIs? For understanding, for our purpose, we have to get a 0-1 assignment to the x's. Now, here there are various techniques to solve it, and I'm just giving you one of them. This is by no stretch the only option, but here is it, that assign xi equals to 1 with probability pi and 0 otherwise. Now, this basically means that I first solve the relaxed LP, get the solutions, and depending on the fractional values of the variable that I get a 0-1 assignment. And one thing to see is that the expected return, now for people who are familiar with probability, I am talking about the expected return. If you are not familiar with probability, don't worry, this is not something to be too much harassed about. It basically says that this still gives us a reasonably good solution. It basically says that on expectation, this is a pretty good solution and we get a good output. Now, the main reason why I started this problem is that To pick up this example is that, again, this is an example where you took the problem, you converted to an LP, you could not solve the LP, but still there was the whole literature using which you can still get a good enough answer to the LP using various techniques. So, in general, whenever you have to solve a problem, a good technique too is that how can I use mathematical languages to solve these problems or reduce these problems or model these problems. And LP is one of those nice tools to have. Now, the good thing of this thing is that the LP solver gives us optimum solutions, the LP solver gives us optimum solution over reals. But if we have an integer linear program, then we can somehow get a solution that is not too bad from the optimum solution. And this basically talks about a new kind of algorithm called the approximation algorithm. I don't want to go into it. This is not in the scope of this particular subject. Now, why is the integral solution harder to get than a real solution? Let me not go into it too much, but this is one of the examples that this is a picture that kind of just explains why finding an integral solution can be a harder job than finding a real solution. So anyways, wrapping up, many optimization problems can be formulated as linear programs. Linear programs over reals can be solved quickly. If the linear program is over integers, then one can relax it to get a linear program over reals and then make some use of that linear, the solution for the linear program over reals to understand something about the actual problem. So this is a quick introduction for you guys to how to model using linear programming. Let me also say that this is a very rich area of research and a completely different course is possibly required for this thing. Okay. There are certain other various form conditions that can be used to handle this optimization problem, and I am not going to talk too much about it. Now we are still left with these two problems, the telephone tower problem and the meeting scheduling problem. We will be discussing these two top problems in the next video. Thank you.